Let's consider a series of simple events. We've got a man in a rocket ship who fires a laser beam, a single pulse of light, which goes away, hits a mirror, comes back, and is received where he fired it. The light's just gone there and back, so the total distance traveled is just the speed of light times the time it took, which I'm going to call delta tau, and the distance to the mirror is just half of that distance, so it's the speed of light, delta tau, over 2. Simple, no complications. But now suppose that we were to look at that not from the frame of the reference of the guy in the rocket, but instead from the frame of reference of a person on the ground watching the rocket. The event to the rocket man is still the same, but the event to the guy on the ground is different because the light has to travel a further distance. A and B are separated by a great distance. So the light travels this entire diagonal distance up here and back down. Now, normally, if we were talking about a man tossing a ball, we would simply say that because we're in a frame of reference moving with respect to the original frame of reference, this object has to move a further distance, so it's going faster. But that doesn't work, because remember we said the speed of light is constant in all frames. So since the speed of light is the same, then this time has to be longer in order to make up for the longer distance. In other words, more time has passed for the person in the laboratory frame than has passed for the person in the rocket frame. This is not just semantics. There really is more time passing in the laboratory frame. Time is no longer absolute. The change in time here, delta tau, and the change in time here, delta t, are not the same. Now here, this distance traveled by the rocket ship, it's just delta x, and that's just delta x is equal to v delta t, the time in the laboratory frame. However, we're going to focus on this as being just a distance delta x. Later we'll turn it into v delta t and see what results we get. Now, you'll look here and see that half of the displacement, delta x over 2, the long side, c delta t over 2, and the direct path in the rocket frame, c delta tau over 2, all form the sides of a right triangle. So we can use that right triangle and the Pythagorean theorem to come up with an interesting relationship between delta t and delta tau. So we know that the hypotenuse, c delta t over 2 squared, has to equal the sum of the other two sides squared. That's c delta tau over 2 squared plus delta x over 2 squared. Now notice they all have a 2 in them, so that cancels. And I can isolate c delta tau, and I get this result right here. C times delta tau squared, where delta tau is the time in the rest frame, the point of view of the actual person firing the light. That equals c times the change in time in a frame watching this guy move minus how far it moves squared. This is known as a squared space-time interval. And it's one of the most important concepts in relativity. In particular, this is something known as an invariant. This quantity, how much time passed on the clock of the guy actually making the observation, as he sent the light away, came back. He's not moving in his own frame of reference. That's unique because in his own frame of reference, he's not moving. That's special. So this quantity is invariant, which means this part here is invariant. It stays the same in all frames of reference.